fixed wireless access in addition to the small cell base station product for 5G communication. At MediaTek, he was a technical director driving the advanced development in 4G and radar system from concept to the product. He also served as a chief architect of RF group in Semiconductor for their cellular and connectivity products, and as a principal researcher at BlackBerry to develop a innovative SDR in 700 to 5,000 megahertz. He was a distinguished member of technical staff at TI and a key developer of the TI's DPM-TM digital RF processing technology for over 10 years and led the design team of 2G and 3G ERP radios, authoring over 60 patents on a various aspects of this technology. Dr. Khurram Mohammed, you are welcome to start. Thank you very much for your time and your time taking for this seminar and connecting to our students. Welcome.
Thank you. Bismillah ar-Rahman ar-Rahim. So I will share the presentation. So let me know if you can see it. Can you see the screen?
Yes, very clear, please.
Okay, so for this meeting, I was trying to figure out what should I talk about. And since it's the first time I'm talking to a lot of students, I think what would be an interesting start, because I think these kind of talks, they should continue over, on a regular basis in order to guide the students in terms of how they should focus their energies, and also to have some trust in that if they work towards a goal, eventually they are going to get there, right? But the key thing is to consistently work and to set your goals. And if there are some other issues that come in the way, then work them out, but continue, right? So you have to consistently work. But before we get to that point, I would tell you the outline of this this talk. I would go over the current state of semiconductor industry, because I think you may have had a lot of presentations so far, but I would try to put together kind of like how things are in this industry and where things are moving. And then basically, how do you, like what do you do about it, right? So you have to understand that how the cycle of innovation works. So if in future, some of you may want to do your own company, you have to basically understand the process. So understanding the process, understanding how things work is a very critical thing in order for you to kind of to basically plan and continue to put in consistent work. So I will start my talk. So basically, I have taken a lot of material from these three reports. Basically, this is SIA is a organization in United States which publishes the status of semiconductor industry. And since the COVID hit the world, basically there has been a lot of discussion on basically what the policy. Are you still able to hear me? Yes.
We can hear you, but we cannot see your slides moving around.
Oh, I see.
No? Okay.
Okay, so can you see the slides now?
Yes, we can.
Very good. Okay, so since this the situation changing from COVID, basically there has been a shift in the supply chain of because of a lot of lockdowns and lot of things happening around the planet. And because of that, basically the entire industry is revisited, and the government in United States is trying to bring manufacturing back in America in order to have better control over their future. And as a consequence of that, decadal plan, which is basically a decade for one, so basically the next 10-year plan for semiconductor has also been put together from SRC, which is one of the premier organizations that funds research in universities, to basically set out the direction for what are the things that are important to the semiconductor industry in the next 10 years. So I will quickly go over a few slides, okay, just to give you a kind of a feel for what is this industry, why is it important, and why it has become a part of national security, right, for a lot of Western countries. So this industry provides jobs, very high-paying jobs, to about 250,000 people. And one semiconductor job supports 5.7 other jobs. So there are about 1.6 million jobs which are related, not directly semiconductor jobs, but related jobs to semiconductors. And it is one of the backbones of the economy. Okay. In this 2020, $49 billion worth of semiconductors were exported. So it ranks like number 4, right after oil. Right?
Your slides are not. Your slides are not switching. Can you make sure that you are on the slide? Please tell which slide you are in. Slide 4.
I am on slide 4.
Yeah. So we are not seeing slide 4.
Okay. So let me see if I need to share again. Okay. Are you able to see now?
Yes.
Okay. Good. Good. Okay. I think I was on the other screen. Okay. So,
Dr. Khurram, could you please show the presentation mode, because the slides are slightly smaller in this mode.
Okay. Is it good now? Can you see it?
No, your slides are going in the other screen. It seems to be.
Okay. So that's gonna be interesting, because I don't think I was given a. Let me try and share again. Okay, I think now it should be okay. 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 Can you see the full screen now?
Yes, thank you.
Okay, very good. Okay, so I'm on slide 4. I was talking about semiconductor being the 4th largest area. And fundamentally, it is an enabling technology, which means that for a lot of applications, such as Internet of Things, gaming, military, storage, computers, laptops, right? All of these industries depend on ICs. So basically, it is the backbone of the economy right now. The reason why this field offers a lot of jobs is because it is a growing field, right? So this shows basically that for different pieces of market, so basically you have tablets, you have servers, you have medical devices, automotive, so different ICs target different areas, right, or markets. And basically, they constantly are growing. So there is more and more demand as each year passes by. So from 2016 to 2021, what we saw was that there is very high increase. So this is like a compound annual growth rate. So it's like compound interest. So basically, similar kind of an idea that how there is growth from year to year. And because of that, you can see that there is more revenue as every year passes by. And therefore, because of that, there are more and more jobs. And the skills in this area are internationally valued. So if you are able to do a great design, it doesn't matter where you are, right? You will find someone who would want your skills to be put in their products, right? So this is a very, very valued area because there is a lot of competition, there's a lot of growth, there's a lot of demand for devices. And you might have seen the presentation from Facebook, which is now called Meta. And they are now challenging, they are pushing even more use of devices in future to do very, very interesting stuff, right? So the key thing is that no matter what the application is, fundamental know-how, fundamental knowledge is very, very critical. So I will talk about that a little bit later. So why is that you have so much growth? It's because that fundamentally the process in semiconductor technology is that from 1969 all the way to now, the wafers on which the semiconductor ICs are built, they have been trying to make them bigger and bigger. So the reason is that if you have a bigger wafer, then more ICs come out of it. And if more ICs come out of it, then you can actually drop the price because now for the same engineering effort, which is the design, taking out the fabrication cost, but for the same engineering effort, you are able to get more devices out of a wafer. Therefore, you can drop the price and still make a lot of profit. And this is the reason that now you can flood the market with lots of devices and lots of equipment can be built, and then basically you can market it, and it's not something where the prices are in the way of purchasing the equipment. At the same time, from 70s all the way to 2020, the feature size has also reduced. So not just that you have the wafers becoming bigger, the dimensions have become smaller. So now you are able to shrink the same device that you used to build 10 years ago. You can actually build it in a much smaller size. So the same IC is much smaller and it's sitting on a much bigger wafer. Therefore, you are able to produce a lot of them, and then the price actually is reduced. So that is the driver, which basically is the reason for such a high usage of these ICs. In terms of so 2019 sales and breakdown, so we don't have these numbers easily available for 2020 and 2021, but in 2019, half of the total semiconductor industry, basically, this half of the sales was happening in United States, and about the same in the rest of the world. So you can see that United States is a very, very big market. Okay, so if you build something, people who are going to buy are sitting here. Okay, half of them are here, about 20% are in South Korea, 10% in Japan. So over the past 20 years, they have been making a lot of effort to have more and more Chinese customers, and they have been very successful at that. But there is a lot of so this is a huge topic that how does that work out? So I will not go into that, but basically what I'm trying to say is that that this is an area where still Europe and United States have most customers or consumers of this market or this industry. The biggest part is logic and memory. Okay, so logic and memory is basically 2/3 of the overall ICs. And logic would be like processor and all the digital ICs, right? Networking ICs. So everything which is sitting on a digital node, that as well as the memory is where most of the ICs are. And analog is about 13% of the overall pie, right? So if you work in analog design, you should be aware that the market size is going to be smaller compared to the overall market size of digital. Therefore, a lot of people work in the digital side. And of course, there is discrete devices, which is basically like optoelectronics, sensors, diodes, the old traditional devices. And over there, still you can see Japan holds about 25% and Europe holds about 42%. So most of the energy is in the first three areas. And also to give you an idea of what are the big companies, the top 15 companies. So Intel, Samsung, TSMC, SK Hynix, Micron, Broadcom, Qualcomm, TI, Toshiba, Nvidia, Sony, ST, Infineon, NXP, and MediaTek. These are like the major builders of ICs. They are divided into two types. One that have their fabs and the others which don't have fabs. So they basically are fabless and they only design. They have less control over the actual manufacturing, but they are usually more profitable. So you can later on look at these slides and see that which company is in what area. Memory and logic, there is a little bit of now, so it used to be very specific that you had certain way of doing devices so that they could be reliable. And then they had very nice layout. So you could do like 40 or 60 cells in DRAM. And there are other kinds of memory as well. But fundamentally, now what people are talking about is to have computation also in memory, which I would talk about a little bit later. So there is some new areas which are also developing over there. So I briefly talked about that IDMs, where you have integrated device manufacturer, which means that they have their own fabs. What's this fabless? You can basically see how, basically US, South Korea, Japan, Europe, Taiwan, China, and Singapore are major players. ATP is basically, it stands for, so I will go a little bit later on this, but this is packaging and test and assembly. So basically, Singapore is active here, as well as Taiwan is very active here. So Taiwan runs TSMC, which is a very, very successful foundry. So for fabless firms, usually they are working with Taiwan because they hold a lot of fabs. So the difference between IDMs and fabless is that in a fabless, in a IDM company, they have their own fabrication, so they can control the device. And they can build the overall solution, the chip, with the control of the device. So they can control doping levels, they can make a certain recipe, which may be better for reducing power dissipation or may speed up the process at the cost of more power, but basically the ingredient with which they are building the chips, they have more control over. So that's their differentiation. But when you have a fab, it is a very expensive a piece of equipment. So basically, a fab has to be busy all the time, otherwise it produces a lot of loss. So as a result, they have to not just, so they have the advantage that they can have a special recipe, but they need to build ICs which take advantage of that and are differentiated enough so people would go after them rather than what is coming from a fabless company. So it is not easy to be a IDM, okay, because of the reason that not just you have to have special recipe, but the solution that comes out as a result of that special recipe has to beat the solution which is coming from a fabless firm. And you have, if you are unable to do that, then your fabs are not running around the clock, which is creating a lot of loss. So as a result, for a fabless company, which is a lot of companies, right? So basically, Broadcom, Qualcomm, NVIDIA, ST, I think also does not have their own fabs, and NXP. So they are all fabless companies, so they have more profit margin, and their earning is less volatile, meaning that from quarter to quarter, they are able to make good earning. So good earning means that people over there have more stable jobs, right? And if you have not good earning, it means that it becomes a problem in terms of like keeping the morale of the people high, right? Because if you are not able to make good profit, then you are competitively seen in a worse place. So basically, if you now look at that, okay, so this is kind of like the overall picture that you have these companies, some are fabless, some have fabs, and then in order for, and this is a very, very valuable area to work in, but a lot of things have to, come together in the right way in order for you to actually be able to sell your device, your solution, as well as make profit, right? So you can see that this is not, when you consider that Intel has world's most advanced fab, then there is a lot of work which is going round the clock to keep it that way, right? It is very easy to become less competitive if you are not putting in enough effort. In terms of the different activities, so this is there are some areas which are R&D intensive and some areas which are CapEx intensive. So CapEx intensive means that you have to put a lot of capital expenditure. Okay, so that means you have to put in a lot of money in order to build what you are building. And R&D intensive is EDA, which is the simulators. So Cadence, Synopsys, even the software for fabricating devices. So basically, United States is the foremost company, and Europe is the foremost company. Have the foremost companies in basically the intelligence or the smart, software with which everything is built. You can see that they have complete leadership. So all the simulators are basically coming from the West. In logic, of course, you have about 2/3 of the leadership is in United States, and rest is distributed. So you can see that, for example, China has very little part in logic, and West has pretty much most of the part. And these are the discrete and optical, memory, and then manufacturing equipment is basically the equipment with which you are able to build the chips, which is the the fabs. So even in building the fabs, it is mostly the equipment is coming from United States, Taiwan, and actually, I'm sorry, this is not Taiwan, this is Japan. So Japan, United States, and Europe. So basically the equipment with which you build fabs, that know-how is mostly in the West, just as the software with which you design, these fabrications or the circuit, right? Fabs or as well as the circuits. So all of the leadership is in United States and in Europe, right? And of course in Japan. For the materials, because this is kind of more labor intensive, this is less in the West, and this is where we got a big jolt after the because of the lockdown due to COVID, that the supply chain got disturbed, and because of that, the cost of semiconductor went up because it was disrupted. You can see also that the assembly and packaging, because this is manual, it's not manual, but it is not a high return. It is mostly done outside. So China had a lot of part of that. So basically that gives you an idea that where, there is special know-how. Again, you will see that on the special know-how, West is much ahead. It has all the market share. But in manufacturing, you will see that the rest of the world has a lot of part because manufacturing was not considered to be a high return business, right? Till COVID happened. So this is, a slide that basically goes over overall process that, you have raw materials, and then basically you have design activity, and then you do the fabrication, and then basically you go over it. So basically this is, you can look at this and see that on the world, where are mostly these activities going? And you would realize that basically, this whole thing is very global, right? That you have not just US and Europe, but around the world, everyone works together to build you, to bring you the products that you are able to use. The main thing I want as a takeaway from this slide, other than its educational value, is that 90% of the value of a semiconductor chip is between the design and the fabrication. Okay, and 10% is value added, which is basically back-end assembly, test, and packaging. So as I explained in my earlier slide, that's why assembly, testing, packaging have been outsourced long time ago from the West, because it does not bring you a lot of return. But most of the return is coming from basically designing the ICs and then fabricating the ICs. And fabrication is mostly done in Taiwan. So basically, as we see that over the past, like from 1990, when 37% of manufacturing used to be done in US, it went down to 12% in 2020. But now there is a push to bring back a lot of that manufacturing back in US, so that there is more self-reliance on building the ICs, because The future requires that you should have, basically there will be more reliance on semiconductor ICs. So basically, from here you can see that in the future, there will be more manufacturing done in the West, right? So if you see that all the manufacturing is done in South Korea and in Taiwan today, that doesn't mean that it is going to stay like that forever, right? There are changes on the horizon. So you have to kind of realize that and understand that the know-how, the best technology minds are actually sitting in a lot of places in the West. So, and they are trying to bring it back. So it is important to be aware of that. Now, of course, there are high R&D costs. So this is very important for students because R&D means jobs, right? So a lot of people, when they are trying to get into a field, they should look at what kind of research and development funding is there. So just below biotechnology and pharmaceuticals is semiconductor industry. It is even more than software industry in terms of the percent of what is spent in R&D. So what would be R&D? It would be that when you scale down, then you have to build the same circuits on a smaller feature size process. So that is one part of the research. Then basically creating the models, improving the CAD software to basically deal with the physics of shrinking down, right? Because a lot of things happen. It's not the same algorithms which were running before may need to be improved. So so on all fronts, on EDA tools, on fabrication, and also on the circuit design, you have to start again on a new process node where everything is now smaller, right? The feature size is smaller, and then basically you have to understand that how do you get performance out of that? So basically, this is the reason why this area always has very, very high R&D expense. And you would see that most of the expense, basically most of the jobs are in US, Europe, and Japan, right? And this is the area which is the most lucrative. So you would see that 90% of the value of this field is actually in this area, right? So therefore, it sees a lot of investment in terms of R&D. In terms of manufacturing, this will change, but right now, California, Texas, and Oregon are basically the places where most of the semiconductor work is done. So Texas has a lot of activity. We have in the area in the north side, we have lots of companies like TI, and then in Austin there are lots of companies. We have traditionally Silicon Valley is in California, and then we have San Diego, and we have the area of Oregon. So basically, this is where most of the jobs are because the big companies are sitting over here. And in terms of fabrication process, in the past, basically up to 2019, this is before COVID, most of the sub 10 nanometer fabrication was in Taiwan. So you can see that below 10 nanometer, Taiwan has 92% of world's share, and South Korea has 8%, right? And this picture with time is going to change because of the realization that a lot of manufacturing needs to be brought back into the United States. So we have one fab which is getting built by Samsung in Austin, and another one in Arizona is built by, I believe, TSMC. So slowly fabs are going to come back into United States. So that with this, I will basically kind of wrap up that, okay, what I want you to get out of it is that understand that there is knowledge and there is work needed to do to basically put things together. And knowledge has different levels. So the upper level of know-how, where you have to figure things out, where you combine physics and maths and a lot of intuition, it is mostly done in the West. And because of the last 2 years, they realized that maybe they had outsourced too much. So they are going to kind of like scale back on outsourcing. So in future, basically, there will be a push towards more manufacturing in the West for security reasons. So that is one thing to understand. And on the other side, China is trying to grow more into these areas, but so far, basically, most of the value is in the know-how that is in the West. Okay. Now I will talk about what is the vision for the future. So SRC put together this decadal. So I will briefly describe what are the things that they are focused on. And there's a very commonly quoted quote from Abraham Lincoln that the best way to predict your future is to create it. So what that means is that in order for you to be able to create your future, right, to predict your future, you figure out what you want to do and then you go in that direction, right? So SRC puts together this these kind of plans which span 10 years. They pour in about $2.2 billion. They fund 3,700 research projects in university. And the goal is that they set the research priorities in different areas like information processing, sensing, communication, storage, and security. And the goal is that they want to have sustainable growth in the semiconductor industry. And they support basically they come up with these strategic visions for not just semiconductor companies, but also for government agencies, so that there is a evolution in the research programs, and basically they set the direction of what they think is important. So according to their latest decadal plan, there are 5 areas where there is going to be a lot of shift in analog design. So I have been looking at ISSCC for, I think, around 21 years now. And what I have seen now is that there has been a shift, and you can see in ISSCC as well, that a lot of traditional areas, publications are now, the type of publications that are appearing are changing. So the reason is that for the future, there will be a lot of sensors. So basically, there will be a lot of analog data captured from the sensors all around us. And there is the traditional way of building devices is not going to work, because there will be too much demand on communicating a lot of data from sensors to where the decision is made, right? So basically a way to deal with a lot of data which is coming from a lot of sensors around us. The growth of memory, basically memory scaling is also is reaching its limits. So basically there is a requirement to come up with new memory structures, new ways of storage, which can accommodate the requirements for the future. And then having communication capacity versus data generation, meaning that if you have a lot of sensors and you are communicating all of that data, then basically you don't have enough communication capacity. So you need to improve your communication networks and basically deal with ways to not require communicating a lot of data. So the sensors need to become more intelligent. That's what it really means. So not just that you need to have higher capacity communication, but at the same time, you need to kind of like have new ways of thinking that how can you make local decisions in the sensor. So sensors need to become smarter. And then there are security challenges where someone can basically interfere with what your device is trying to do. And there are lots of security holes created. So basically ways of dealing with those. And then basically in reducing the energy consumption, because as the device is increased, one of the problems is that if you just calculate how much energy is required to power all of those sensors and devices and decision-making devices, then the global energy production is not enough to what the capacity is in terms of building these devices and empowering them. So I will very quickly go over each one of them. So basically, in analog electronics, basically analog is what interfaces us with the physical world, and you have a lot of areas in which analog works, right? You have A to D, D to A converters, then all kinds of power devices, which is regulators, linear regulators, switch regulators, instrumentation, computation. So lots of areas where you have analog electronics, but you need to now think of not just doing analog to digital conversion, but analog or basically sensing to information conversion. So this concept is that instead of doing just converting something from analog to digital, you need a new way of thinking where the A to D is not just giving you digital bits, because now you have a lot of digital bits coming from a lot of sensors, and then they need to be absorbed by something where the decisions are made, right? So basically, when you do the math, you will see that it is not sustainable. Therefore, what they want new researchers to think about is that how can you convert an analog sensed information or sense signal to information, right? And at the next level, basically to action, that the sensor can locally make a decision and take an action. So you can think of it this way, that if you are trying to touch, like a robot's finger has sensors and it is trying to touch something and hold it, then do you want all the sensor data to go all the way to the central control unit, or do you want that tactile, basically the feeling of pressure, because you have to hold things with a different pressure depending on their weight and depending on what you are trying to do with it, right? So basically, the decisions, should they be made locally without the need to transfer a lot of data, or and basically, can we actually take the action right there and then, right? So within the sensor, you can create the intelligence, the smartness to take an action rather than communicate all the sensor data to some central location, spend energy on doing that, and then also have a lot of data come to some decision device. So there are lots of, so basically all of this is inspired by like how people, like how humans work, that we don't want everything to be brought into the central brain in order to do the processing. A lot of nerves are, they are in all of our, all of our body, where they can produce some sensation with which we can react. Also, on the communication side, moving into the terahertz regime, so building ICs that can actually produce viable communication systems in terahertz, which is actually usually like 100 gigahertz to 300 gigahertz. And also on the software side, on some kind of a development methodology. So basically the goal is that how do you do sensing and analog together, augmented with machine learning in a holistic way, so as you can make intelligent decisions right where you are sensing the information. Okay, that's in a nutshell one of the areas, right? So this applies, of course, to all kinds of sensing, right? So you have video and you have so you can imagine any sensor, and this analog to digital is basically like a way of thinking that you sense something which is in the analog domain and you have converted into a form where it is processed. On the other second theme, basically for growth of memory and storage demands, basically, as I briefly mentioned, that the scaling of memory is going to stall because already the feature sizes are very small. And for the information and communication technologies, which is ICT, because of lots of sensors all around us, right? We are expected to see enormous amount of data which will be generated, and storage of that, especially like in terms of artificial intelligence, is it will become a challenge. So basically, fast, dense, cost-effective, embedded, non-volatile memories, and then memory and storage for new information representation. So meaning that there will be a push for doing computation in memory. So you can, instead of just storing it raw, you would store the actual information instead of just the data. And then there is a lot of work which is also pushed for quantum computing, and how would you design memories for that, and some other new storage technologies. So basically there's a push also on the memory and the storage. Similarly, on the communication side, there will be more push on the millimeter wave, on MIMO with thousands of antennas. So this will produce very sharp laser-like beams. So you can basically have lot of users in a small area carrying very, very high capacity. And basically this will be to support the needed capacity to support AR in virtual meetings and smart offices in future. So if you look at Meta's presentation, you will get an idea of what the vision is. And in order to support that vision, you need a lot of communication technology to support all that data transfer. And also with all of this comes security challenges, that the devices, the solutions that you are building, they cannot be easily hacked into. and made ineffective. So basically, imagine that you are relying on a complete system where you have lots of sensors and you have decisions going on privately, and you have lots of data which is being stored in memories, and then there are decisions being taken, and some of it gets hacked, and that can actually make the whole system completely ineffective. So new cryptographic techniques are also going to be developed to make ICs more reliable and basically secure against threats. And finally, there is the area of low power. So basically, as we see as I kind of like referred that in the area of general purpose computing, as the computing grows exponentially, basically the power required to power everything up, the needed power will double. This is the estimate from SRC every 3 years. But the world's energy production is kind of not growing that much. So basically, at some point, if you try to, for example, I'll give you one example, that if you build a 300 gigahertz infrastructure, and at 300 gigahertz, there's a lot of propagation loss. So the base stations have to be placed very close together, right? So you get this enormous capacity. You can actually maybe do 100 gigabits per second to each user in your area. But if you do the math and you look at how much power is required in order to power those base stations, in order to sustain all of that communication, you will see that the energy supply to the city is smaller than what you will be needing, right? So this is a huge problem. So because of that, we need to think through how to make these systems more energy efficient. Okay. So that was basically a kind of run up to introduce, give you a picture of what the semiconductor area is like, and then what are the future areas where one of the major organization in America is projecting that we need to advance the circuits. And you would see that a lot of these areas, you would start to see publications appear in years starting from, I think, already in this year. I looked at papers where compute in memory has come into picture, and also trying to embed AI in sensing has also taken off. So you would see more and more of it. So at this point, I will make a break and see if anyone has any questions. And then we can continue to the rest of the topic.
Hello.
Yes.
You can hear me?
Yes, I can hear.
I am Shahzeb, and I am doing my PhD from University of Florida, and I am in my first semester. So my question is related to heterogeneous integration. Then how industry is seeing, and what would be the future on the career perspective in this field, like the heterogeneous integration in the RF circuit especially.
Yeah, so okay, so for these very specific, I think we should maybe set a more dedicated session, but all of this is in its infancy. Okay, so right now these organizations like SRC are setting up a direction, right? But we have to figure out that how do you, like, there will be different proposals coming, and it's not going to be very clear on how everything comes together. But over the years, it will become easier. It's not an easy thing, as you know that when you have integration of such level, then security challenges are also very, very critical, right? So it's not just the technology, but also that is that technology safe to deploy, right? So I think that for these kind of areas will see a lot of work. But I don't think industry has a vision right now of how everything will come together.
Thank you.
Okay, so maybe I can then continue on the next topic, which is to introduce the cycle of innovation. Okay, so cycle of innovation is very important in terms of like from the perspective of students. I think it is a good idea to help them understand that what exactly happens. So there was a time when a lot of research was sponsored by big corporations, and that time has passed. And now is the time where people who have good ideas, they create their own startups, and companies that actually have good ideas and are able to make something which is useful are basically acquired by big corporations. So this is where things are at right now. So I will kind of go a little bit into this, that the way to go around innovation is that you go from an idea, then you have to figure out how that idea will go to the market, and then what you would compete against, what would be the resources that you require. Okay, for example, in resource you have time, how much time would be needed, what kind of people are needed, and then what kind of capital expense is needed in order to convert time and people into the product, right? Into something which is a manifestation of the idea. And then basically that is what is covered in execution and pivoting. And then if everything goes well, then you have to scale the business. So first of all, with all of these, push in the industry, you have to come up with a concept, right? And that concept is basically that, okay, what is it that you want to do? And then how would you do it, right? So basically, if you are trying to build a new kind of a sensor, right? So what sensor, so for example, somebody says, well, I want to now go into 300 gigahertz and I want to build a better sensor, right? And I'll make my startup and I'll make those sensors, and then they will have higher resolution, because at 300 gigahertz, I have much more bandwidth available. So with more bandwidth, I can get more resolution, okay, in range. And then at 300 gigahertz, the antennas are smaller, right? And the the antenna to antenna separation in an array is also smaller. So for the same size of a radar, I can put more sensors in there, right? So if you have 77 gig versus 300 gig, there's a factor of about 4. So you can pack 4 times more antennas into the same form factor. Therefore, you can have better angle of arrival and you can have better, range. So basically, you have to describe that how you will achieve it, and then basically, okay, if you build it, then how will you generate? Like, where will this sensor be useful, right? Because of course, if you do a 300 gigahertz sensor, then when you go into the physics of the devices, you are going to learn that, well, I cannot produce as much power as I can produce with 77 gigahertz. So of course, you gave up the range, right? You gave up the range because the physics is telling you that you cannot generate so much power as you could generate at 77 gigahertz, you cannot generate that much at 300 gigahertz. So therefore, what would be the use case of this idea, right? In the go-to-market strategy, basically, you have to figure out that with your idea, who will be the end customer, how it will benefit them, and most important question is that if they take that idea, right, if you are successful, then how do they make money from this idea? This is key, right? If they are not going to benefit from this, why should they take your invention? So this is the most important part. Usually, inventors are very excited about the technology that they are developing because it is hard. Maybe it is first in the world. So it has a lot of value in terms of, impressing everyone around them that they are capable of doing something really spectacular. But if it does not create money to an end customer, then there is no buyer for that, okay? So you have to kind of go through that process before you actually work on the idea and make a first prototype. You have to go through the process to understand who will use it and how will they benefit from it, and then is the benefit big enough so that they are persuaded to use this idea. Okay, so this is very, very critical. Then the next question is that for what you are suggesting, right, what your idea is, who are the other players and what are the competing technologies? And then how does your idea give a differentiation? So meaning that suppose that now you have a 300 gigahertz sensor, right? And you figure out that, okay, I have great, thing about it is that it can work whether it is day or night, and also if the environment around it has a lot of fog or it's not clear weather, this is still going to beat, for example, a camera. But then if the range is smaller, then what happens is that now you have to compete against ultrasound, for example, right? Because that also is using a different technology, but it has very, very good resolution. So then you have to figure out that why is your sensor better than the other sensor, right? So how would it be better? So once you are convinced about that, what you are trying to do is better and it can benefit an end customer and the benefit is large enough so that they will be persuaded, then comes the execution, right? Meaning that you have to now figure out that how would you develop it? So basically, to show the feasibility, which may be just simulations, right? How do you demonstrate the feasibility? How do you build a proof of concept, which is also abbreviated as POC? So how do you build the first prototype, which proves that your idea actually is, it does what you think it does, and then convert it into what is called a minimum viable product. So basically, build something which is simple enough, not very complicated, not very complex as a commercial product, but it demonstrates the idea in the best light that you can with a reasonable amount of time and resource. But then you need to understand that what kind of skill set people are needed and what equipment and support software is needed. So this is the reason why software companies are much easier to build, because it is about idea and skill set. And equipment and support software in IC design is extremely expensive. Therefore, hardware companies are capital heavy. And basically to get to the first proof of concept prototype or a minimum viable product, you do have to invest a lot of money. So then basically comes execution, where you actually go through the steps, you show the feasibility, you build a prototype, and then you do the development of the minimum viable product. And then basically comes the first learning, where you show it to your customer, and the customer tells you what actually the customer wants, right? So you had some idea that what is important to the customer, and you build something, and then you get the feedback from the customer that there are some assumptions that you had incorrect. So basically that learning creates the modification of the original solution. So this is the reason that a lot of startups, hardware startups, engage with the customers early on, so that they can get the feedback early on, so that they have less time, they require less time to be able to build a minimum viable product, which is useful to the customer. Okay, so this is a very, very critical thing. It's not just the technology, but there is a lot of interaction and outside of technology work that needs to go in order to build something which is useful to someone. So the other reasons why you may need to modify the original solution is that you may find that you were more aggressive in considering that your idea is really good, but you found that it is not really that good. So maybe, or maybe there are major roadblocks which make that idea not implementable. So that way, that is another reason why people have to go in and modify the original solution, and that is what is called pivoting. So pivoting is very frequent in startups, that they come up with something and then they figure out that either after building they get the feedback from customer, which requires them to modify the design, or their idea has issues and they have to go around this and they have to basically change their original solution to accommodate the new realities. And the third one is that you may have a changing business environment. So if you were targeting certain customers or certain part of the industry, that industry goes through a financial crisis, for example. And because of that reason, what you are trying to do, the customers are no longer investing, basically in the direction where you initially were considering. But if none of that happens and you build a MVP, you engage with the customer early on. So first identify customer, engage with them early on, get the right requirements from them and build an MVP. And then the MVP is good and they like it, then they may actually ask you to give them that product. And then you go from the mode of an innovator to a product company. And this is the hardest transition for any startup, which is going from the mode where they are developing technology to becoming a product company, where they have to do volume production, they have to maintain the quality, they have to work with the customer in order to keep them happy with the quality, and then executing in a way, so basically doing all of this thing in a way that they are sustainable, so not burning too much cash in doing that. So these are the fundamental steps in terms of the of building these startups and going through innovation. Now, even if you are in a big company and you are trying to do exactly the same thing, so even if you have jobs and you are trying to build something which is new, exactly this is the cycle, that you have to build a minimum viable product, and from the product to mass production, you go from innovation into a product development cycle, and it is equally tough over there. Now, one of the key things to understand, compared to software startup, hardware startups are harder. So you have to love what you do, right? You have to enjoy what is involved in that. The important thing is that each time when you raise the money, right? So you have great idea, you have great customer, and you raise the money in order to get the capital expenditure, right? Basically, every time you raise the money, your ownership becomes less and less. So in the best case, the founders and the employees, they keep a major share. So that means that they keep the control of their destiny. And in the worst case, the founders become employees, meaning that every time that they are going through raising the capital, their own ownership becomes diluted and diluted and diluted. So you go series A, B, C, D, E, and each time basically their own share becomes more and more diluted. So in the worst case, your share becomes almost the same as if you were working for a startup and you were given some stock options, right? So, and in the best case, you have, the founders and the employees, they keep the major share. So the best approach is to use as little outside money as possible. So these are the things that are very important to learn early on. Okay. So this is basically like kind of like an overview of like when you think of this innovation cycle. The innovation cycle can happen as an employee of a company, or it can happen outside of a company as a startup. But they're, both of them have their own challenges. But usually the key thing is that from idea to the use of that idea in a product, there are lots of steps and phases. And it is very important to understand what are the trade-offs. And usually the best way is not to take money from anyone, which is what really happens, which can happen in a software company, right? So for example, if you build an EDA company, right? So you are building algorithms to address, for example, there was a company, Magma, long time ago. And what they did was that they took a layout, and from the layout, they would actually, they developed algorithms to look at the critical paths. And then the algorithm started to shave off, basically change the buffering, change the layout a little bit on the critical paths so that the critical paths become faster. So basically, as the critical paths become faster, then something else becomes a critical path. So they were able to shave off, maybe like they could improve the maximum speed by 15%. So if you got a cadence layout, and the layout, it could run at 300 megahertz. Then after you took that layout and you ran through, so this software had no idea what it was, but it only took the netlist and the layout and figured out the critical paths, and then it shaved off the critical paths, only focusing on the critical paths, and modified with these new, more advanced algorithms, they were able to increase the speed. And that was a huge plus for them. So for this, they only needed people and algorithms, right? They did not need any, they did not need to build any hardware, any prototype, but they built the software. So that area still is considered as the software side. And in a hardware kind of a setup, and that still is easier to invest in. But the know-how that you need is at an upper level, right? It's so designing circuits, designing a system versus the algorithms used to design and make them more efficient. It is a different kind of a skill set. So that's basically one of the things that I wanted to kind of highlight. And finally, I think I'm going to bring it to the close. So in order to achieve excellence, so achieving excellence is very critical in IC design. You learn different aspects of the IC design. Okay, it is going to be a lifelong journey. So you have to acquire the knowledge in order to find the area which is most exciting to you, because there are lots of areas. I showed you the whole snapshot of the industry, that you have EDA tools, you have logic, you have memory, you have analog, and in each of these, there are lots of things going on. So basically, you have to figure out enough so that you can find the thing that really is very exciting to you. Maybe it is computation in memory. Maybe it is making smart sensors where machine learning is embedded in a sensor and it can make decisions, right? But in order to do all of that, you need to actually get enough knowledge. So you have to focus on getting knowledge so that you can find something which is very exciting. The second goal in this learning is that you should be able to connect the physics, mathematics, and intuition. This is very important, that when you are working from process technology to process technology, basically physics start to play a bigger role, and mathematics is a way of accommodating the changing physics, and intuition is where your intelligence works. Basically, everything that you have learned before, you can project it into a future system where you can make the best figure of merit. You can get the best performance out of the new physics paradigm. And then becoming good at what you find most exciting. So when someone says becoming good, it doesn't mean that you have a lot of knowledge or you have skills. There are three things which make a person good. One is the most important is their attitude, right? So if your attitude is that you are always trying to get the best knowledge, learn from others, ask questions, and improve upon this, your understanding of things, acquire knowledge, acquire the skills, and then be able to produce results, then basically that person is considered to be good. So results are very important. Just knowing, just learning something and having the skills is not sufficient. You need to be able to get the know-how to produce results. And then understand the big picture always. So if you are working on something, like I tried to show you how the industry is organized, it is important to understand more of it, so you know what are the things to work on, and then how to approach like solving a problem, like who would be using it, and then what is the the ecosystem of semiconductor industry, right? If you work on something, you work with, say, Estonia, and Estonia is not able to convert that development into something which converts into money, right, or revenue. But if you work with, for example, IMAC, if you have the right kind of partnership, then basically from there you are able to get a better outcome of what you are trying to do. So always understand the big picture in terms of like what the products are about, what is important, what is not important when you are trying to come up with a solution. In the semiconductor industry, good engineers are very valued. It has an enormous need for good people. So basically, you can see that there is a lot of development going on. There is a very big vision of future electronic circuits. So anyone who is good, right, is going to always find a place in this industry, either as a startup, independent of where they are physically located, or becoming an employee of one of the places which is doing something very futuristic. Long-term commitment and constancy is very important. being hands-on is very important. So engineering is always, you learn engineering best when you build something. So build, meaning that even if when you have some idea, simulate it, try to understand it better, try to understand the physics around it, try to understand why it is behaving the way it is behaving, and try to understand where what it is, not good at. The more you learn, the more you will realize that how much more is there to learn. Um, Learn, share knowledge, right? And then teach and improve yourself and learn to think strategically, right? So organize yourself to be able to reuse what you did before. So this is something that it takes a long time for some people to become organized, and they work on many different things. And usually it's a good idea to keep, like, grow your knowledge and be able to build on what you learned before. And most important is to set goals and achieving the goals. Okay, so it's like, the physics equation, work equals to force into displacement, right? So force is your effort and displacement is to achieve a goal. And work is basically the outcome. So basically you have to put in an effort and you have to make a displacement, meaning that you have to do some kind of a progress in order to achieve the goal. And a lot of times what happens in startups is that they know where they want to go. And basically, it is never a straight path. The path goes through different learning cycles, and then they are able to find the end point. And to help all of this, you have to seek advice. So try to get mentorship, try to get mentors, and in terms of the different parts of this activity, there is an individual level where the last slide was covering that. The people who actually spend the energy to create the results and provide leadership, right? And then there are institutions where you have to pool resources so that those resources are used by the individuals in order to succeed, and build partnerships and provide guidance and encouragement to these individuals, right? So basically, what I foresee is that, inshallah, sometime, not in very distant future, we would have an ecosystem even in Pakistan where you have institutions where the resources are there, okay, all kinds of resources, including mentorship, and partnership with the right organizations across the world, so that you have direction that can actually be given to individuals who are actually trying to spend energy and get the results or achieve goals, right? And on a private level, basically this is, people who are working in industry, they can also give mentoring and advice. So in conclusion, I think I talked about many different things, and this is more of an informative session. I hope that it will bring some guidance to some students who are starting off and trying to understand what this area is, what are the challenges in this area. But the overall conclusion is that overall, like in the next decade, you will see that there will be more consolidation of manufacturing. So basically, in order to get a reliable supply chain and for national security concerns, you will have more consolidation in the West. And that is where most R&D happens. And there has to be, an effort to find prospects of collaborating with institutions over there, so that you can build, you can build the resources in order to be able to succeed. And the important thing is that this area is a growing field. It offers many areas of expertise. So you can pick an area and you can become good at it, and you will be a part of the force that propels this industry forward. Okay, it's just going to happen. You don't have to worry about that. But it is a lifelong journey, right? Because everything progresses each year. Okay, so that was my final thought.
Thank you very much, Dr. Khurram Mohammed, for a very engaging talk. I was listening all through and through. So here I have two questions, and then we will ask the participant to ask the question. So first question is about the packaging. In the slide, you mentioned that most of the value is like 80% of the value is in the IC design and then fabrication, and then 20% or 10% into the packaging and the related technologies. In
Yes.
some particular cases, especially when the packages have a more dissipation or more high frequency, it's said that the packaging is more expensive than the silicon die itself. So
Yes,
how
yes.
the two concepts relate to each other?
Right. So, okay. So this is in regards to the overall industry. So what we are talking about is very specialized circuits. And yes, that is correct. In those circuits, the packaging is very expensive. But the know-how to do that packaging and the volume is very low, right? This is one of the challenges that when you are building. So normally, like military uses those very high frequency circuits are not usually their volume is very low. So the overall contribution to the overall dollar from that activity is not very high. Most of the activity is going to be, if you look at, for example, this slide. So most of the activity is, I think so there is a slide where the overall revenue, but basically logic and memory, right? So if you look at very high volume devices, the cost of packaging is very small there. It's not. It's usually not a very significant part. So I think that if you look at the total dollar for very specialized high frequency circuits, high powered circuits, the volume is very low. Therefore, the total amount does not add up to a lot. But most of the packaging revenue is coming from basically these three areas. Right.
Thank you. Thank you very much. My second question relates to the ecosystem in Pakistan. So it's not a question, it's a more of the comment or discussion that in Pakistan, the things has improved a lot in last 2.5 years. And there's fundamentally, there is an interest in integrated circuit design from all the stakeholders involved. For example, in 2019, FAST started the Masters in IC Design with help of NICAP. And now there are 3 other universities in NUST, the alums and EF kids who are offering the master's degree in integrated circuit design. So on the institutional side, the things are changing. There are a lot of community discussion going on. This lecture is one part of that. On other forums and this kind of forums where people have started discussing the IC design, the ecosystem of IC design. The good initiative from government is I want to tell to the student that is the STZs, which are the special technology zones, and they are offering 10-year rebate on the tax and all other things which government charges, a kind of one window operation for the startups. And there is a huge startup in the NUST where they facilitate the startup. There's a startup in Islamabad which is maintained by the government of Pakistan. There is another startup coming up in the Rawalpindi Textile region. Lahore, they are already a startup zone is there. In the Karachi, there is already a startup set up there where the government is mentoring and giving the place and initial guidance to the people who want to start up any company in any area related to software or the electronics or mechanical or anything. So these are the good things which is already in place in the ecosystem. So if the as you rightly advised, if the student engage in the activities which are learning hands-on, and then the basic innovation, and then they learn the ecosystem of entrepreneurship, then in the young, this is the most suitable young age where you can spend 3, 4, 5 years in the startup and try to put up your energies to making something new. So this was my second aspiration. So any other questions or the comments from the audience, you are more than welcome.
Yeah, please feel free to ask. Okay, this is informal discussion, and even if you think that like, don't be discouraged in terms of asking questions.
अस्सलाम वालेकुम डॉक्टर अकरम, हमाद चीमा बोल रहा हूँ नासिक से. क्या हाल है आपका?
वालेकुम सलाम, बिल्कुल फर्स्ट क्लास. आप बताइए.
अच्छा, जस्ट टू बिल्ड ऑन व्हाट डॉक्टर राशिद सेड, मैं आपका ओपिनियन जानना चाह रहा हूँ कि पाकिस्तान जो इस करंट सिचुएशन में एक मोमेंटम बिल्डअप होता नजर आ रहा है गवर्नमेंट साइड से, एकेडमिया साइड से और प्राइवेट सेक्टर साइड से. सो इन योर ओपिनियन हमारा फोकस क्या होना चाहिए फॉर द नेक्स्ट 2 years एंड द नेक्स्ट 5 years, just to not to unfortunately lose the momentum which has happened in the past also 10-11 years ago. So I want to hear your opinion on this.
I think जो different organizations हैं उनका different focus होना चाहिए. पहली चीज ये है कि हर बंदा हर चीज ना करे, ठीक है. जो students हैं उनको बहुत ज़्यादा focus करना चाहिए नॉलेज एक्वायर करने में, और जो यूनिवर्सिटीज़ हैं उनको बहुत ज़्यादा फोकस करना चाहिए उस नॉलेज को पूल करने में और उसको एक्सेस देने में, ठीक है. तो सबसे इम्पॉर्टेंट चीज़ ये है कि नॉलेज तक एक्सेस हो, और वो जो नॉलेज है वो स्टूडेंट्स उसको एक्वायर करें, उससे आगे बढ़ने की कोशिश करें. ये क्योंकि इस हर चीज का जो यानी जो मेन फोर्स है वो इंडिविजुअल है, राइट. जो यहाँ पे मैंने आपको इस स्लाइड में बताया था कि जो इंडिविजुअल्स हैं, जो लोग स्टार्टअप्स बनाएंगे, दे नीड टू हैव आइडियाज, और जो आइडिया अकेला जो है दैट इज नॉट सफिशिएंट. वो आइडिया कैसे रेवेन्यू में कन्वर्ट होगा, वो सारा प्रोसेस बहुत इम्पोर्टेंट है. लेकिन इंस्टीट्यूशंस का जो मेजर फोकस होना चाहिए वो ये होना चाहिए कि वो उस नॉलेज तक को खुद यानी एक्सेस करें और उस तक एक्सेस दें बाकी लोगों को, और वहाँ से गाइडेंस और एनकरेजमेंट, स्पेशली गाइडेंस आए, ताकि जो इंडिविजुअल्स हैं वो सही चीज़ों को अटैक कर सकें. अच्छा, अब जो गवर्नमेंट का जो लेवल है वो बिल्कुल ठीक कर रहे हैं. दे आर डूइंग द राइट थिंग कि वो वहाँ पे आपको इंफ्रास्ट्रक्चर प्रोवाइड कर रहे हैं. तो मोस्ट लाइकली जो पहला लोएस्ट हैंगिंग जो फ्रूट है वो ये है कि आप डिज़ाइन ना करें, बल्कि किसी और ने डिज़ाइन किया है, और लेबर इंटेंसिव अगर उस पर काम करना है, जैसे वेरिफिकेशन का काम है, बेशक एनालॉग वेरिफिकेशन हो, आरएफ वेरिफिकेशन हो, या डिजिटल वेरिफिकेशन हो, या एसओसी की इंटीग्रेशन की वेरिफिकेशन हो, तो वो जो है वो काम इट इज़ लेबर इंटेंसिव. वो उस 10% में फॉल करता है जहाँ पे जो वेस्टर्न कंट्रीज है, they don't really want to spend a lot of capital on people to be doing that work in the West, because it becomes very expensive. So that is the right thing to start off from. उससे ये होगा कि आपका नॉलेज जो है वो امپروو ہوگا کیونکہ جو لوگ اس ایریا میں کام کریں گے ان کے پاس کمرشل سرکٹس یا ریئل سرکٹس ہوں گے جس سے وہ ایشوز کو سمجھیں گے اور پھر وہاں سے ایز اے نیکسٹ اسٹیپ آفٹر اے فیو ایئرس یو ول کم اپ ود اے بیٹر وے آف ڈوئنگ دیٹ. سو اگر آپ لیٹس سے USB 3.0 کو ویریفائی کر رہے ہیں یا کوئی ڈیوائس ہے جس کے اندر بہت سی اس طرح کے پیریفرلز ہیں اور ایک پروسیسر ہے اس کی ویریفیکیشن کر رہے ہیں تو اس پروسیس کے اندر بہت زیادہ لرننگ ہوتی ہے. لیکن جو اینالاگ ڈیزائن ہے یا RF ڈیزائن ہے وہ اس بکٹ میں نہیں فلو کرتا. تو what I would say is in short کہ اس سارے ایریا کو بہت اسٹریٹجکلی دیکھنے کی ضرورت ہے کہ لاجک اینالاگ اور جو ڈفرینٹ ایسپیکٹس ہیں ویریفیکیشن کے ان کو کس طریقے سے آپ علیحدہ طریقے کے ساتھ اٹیک کریں. لیکن جو ڈیزائن ہے وہ اتنی جلدی آنا مشکل ہے کیونکہ ڈیزائن کے لیے انلیس کہ آپ کو کوئی کانٹریکٹ دے دے اور وہ ان کا ڈیزائن بیسیکلی ان کا پروڈکٹ ہو لیکن آپ کو کانٹریکٹ دیں کہ آپ لیٹ سے بہت ہائی اسپیڈ ADC ڈیزائن کر کے ان کو IP دے دیں تو دیٹ مے بی اے پاسبلٹی. لیکن اس پوائنٹ تک پہنچنے کے لیے دیر آر اسٹیپس. تو آئی وڈ سے کہ ناٹ جسٹ کہ یہ سارے زونس کریٹ ہونے چاہیے بلکہ ایک پروسیس بھی ڈیولپ کرنا چاہیے کہ آپ کیسے اپنا جو اسکل ہے وہ جس پوائنٹ پہ آپ ہیں اس پوائنٹ سے لے کے اس پوائنٹ تک لے کے آئیں پاکستان کے انوائرمنٹ میں جہاں پہ آپ انڈیپینڈنٹلی IPs بنا سکیں رائٹ ڈیزائن کر سکیں اور پھر آپ آفر کر سکیں. IP اس وقت آپ کی خریدی جائے گی دو صورتیں ہوتی ہیں. ایک صورت یہ ہوتی ہے کہ اس کا فگر آف میرٹ جو اسٹیٹ آف دی آرٹ ہے اس سے بہتر ہو تو رائٹ اوے وہ آپ سے لوگ خرید لیں گے. اور سیکنڈ صورت یہ ہوتی ہے کہ کسی نے ایک IP ڈیولپ کی ہے اور اس کے کمپیٹیٹر کے پاس وہ IP نہیں ہے تو وہ IP اگر آپ کے پاس ہے تو وہ آپ سے لے لے گا. بے شک وہ اتنی اچھی نہ ہو جتنی اچھی اس کے جو کمپیٹیٹر کے پاس ہے بیکاز دے وانٹ ٹو سیو ٹائم. تو یہ جو تمام ایریا ہے اس میں ایک جو آپ مجھے بتا رہے ہیں وہ ایسے کہ جیسے آپ نے انفراسٹرکچر بنا دیا لیکن اب اس میں کرنا کیا ہے دیٹ از ویری کریٹیکل. اس میں جو چیز RF پہ چلتی ہے وہ اینالاگ بیس بینڈ پہ نہیں چلے گی. اینالاگ بیس بینڈ کا اپنا پروسیس ہوگا, پاور مینجمنٹ کا ایک اپنا سائیکل ہوگا, لاجک کا اپنا سائیکل ہوگا اور جو بڑی SOCs ہیں اس کا ایک اپنا ہوگا. تو ہر ایک اس کے لیے بہت ضروری ہے کہ انسٹیٹیوشنل لیول کے اوپر اور باقی لوگ جو اس طرح کے کام کر رہے ہیں ان کے ساتھ ایک پروسیس ڈیولپ کیا جائے تاکہ آپ اس پوائنٹ تک پہنچ سکیں.
تھینک یو ڈاکٹر خرم. اچھا اس میں آپ نے IPs کی بات کی, یہ ڈاکٹر راشد کے ساتھ ہماری ڈسکشن ہوتی رہتی ہے تو اس میں IP کے جو گیپس ہیں کہ کیا وہ لو ہینگنگ فروٹ اور مے بی ایک چھوٹا سا LDO ہم بنا سکیں اینالاگ یا ڈیجیٹل اور وہ ایک ایز اے IP کسی کو آفر کر سکیں. واٹ از دی میکینزم کہ ہمیں وہ گیپس پتہ چلیں کہ دس از ویئر وی کین اسٹارٹ ڈیولپنگ IP سیلز.
ہاں اچھا اس میں جو سب سے بڑا چیلنج ہے وہ یہ ہے کہ آپ کس پروسیس نوڈ پہ کریں گے. اب کسی کو وہ LDO چاہیے لیکن وہ کسی اور پروسیس نوڈ پہ چاہیے رائٹ. تو اب اگر آپ کے پاس کسی اور پروسیس نوڈ کے اوپر وہ اویلیبل ہیں تو جو ٹائم آپ کو چاہیے ٹرانسلیٹ کرنے کا اس نوڈ پہ جس پہ وہ چاہتے ہیں اس میں دیر از اے ڈیلے, دیر از اے گیپ کیونکہ آپ کو پورٹ کریں گے اور اس کے بعد اس کو ٹیپ آؤٹ کریں گے, پھر وہ واپس آئے گا, پھر اس کو میجر کریں گے, پھر ہو سکتا ہے اس میں کوئی چیز اوپر نیچے اس کو ٹھیک کریں گے. تو اس کا جو ایک طریقہ یہ ہوتا ہے کہ آپ ایز اے یعنی آپ کانٹریکٹ ہاؤس بنا لیں جو کانٹریکٹ کے اوپر چیزیں کریں. مثال کے طور پہ اگر مجھے کوئی IP چاہیے ہے اور مجھے پتا ہو کہ میں یہاں سے لے سکتا ہوں, جیسے انڈیا کی ایک دو کمپنیز ہیں جو اس طرح کی IPs بناتی ہیں So you can actually call them, you can contact them, you can give them the specs, and they will design it for you. But usme catch 22 ये है कि you have to kind of demonstrate your capability. अगर आपकी कैपेबिलिटी आपने डेमोन्स्ट्रेट की है तो आपको काम मिल जाएगा, और फिर वहां से आप अपनी आईपीस आहिस्ता आहिस्ता डेवलप करेंगे और अपना स्किल डेवलप करेंगे. तो इसमें जो सबसे इम्पोर्टेंट चीज़ है वो ये है कि कॉन्टेक्ट्स के थ्रू आपको काम मिल सकता है, देयर इज नो डाउट, लेकिन ओरिजिनली अगर आप कुछ डेमोन्स्ट्रेट करें, कुछ अच्छे सर्किट्स जो हैं उनको टेप आउट करें, उनको मेजर करें और फिर दिखाएं अपनी कैपेबिलिटी, तो you should be able to work as a contract house, और इसी तरह contract जो है after being a contract house for a couple of years, then you will create enough libraries to be able to integrate and build your own product. तो आप अपना प्रोडक्ट हो सकता है अपनी लोकल मार्केट के लिए या अपने जो हमसाए मुल्क हैं उनको एड्रेस करने के लिए you can actually build something on your own. और उसमें जो भी लीगल टर्म्स हैं, जब आप कॉन्ट्रैक्ट हाउस से कोई चीज़ करवाते हैं तो वो उसकी सबसे इम्पोर्टेंट बात ये होती है कि वो कॉन्ट्रैक्ट हाउस ओन करता है लेकिन आपके पास लाइसेंस होता है. ऑलराइट, सो विच इज़ यूजुअली एक्सेप्टेबल कि आप उनको बेसिकली इजाज़त देते हैं कि वही आईपी वो कहीं और इस्तेमाल कर सकें. तो दैट कुड बी वन मॉडल, ठीक है. लेकिन माई पॉइंट इज़ कि हर एरिया फ़र्क है, पावर मैनेजमेंट फ़र्क है और लॉजिक फ़र्क है, सीपीयूज़ फ़र्क है, तो हर चीज़ के लिए एक अलग स्ट्रेटजी होनी चाहिए. तो सबसे इम्पोर्टेंट है डिवाइड एंड कॉन्कर, के डिफरेंट सेक्टर्स को डिफरेंट लोग एड्रेस करें, उसकी ओनरशिप लें और फिर उसको डेडिकेट करें अपने अगले 10-15 साल टू बिल्ड दैट. और इंशाल्लाह आई थिंक कि जैसे जैसे यानी सबसे इम्पोर्टेंट हर चीज़ के पीछे जो है ना, जो इंडिविजुअल्स हैं, हर चीज़ की जो पीछे जो फोर्स है वो लोग होते हैं, ठीक है. इसीलिए सबसे इम्पोर्टेंट ये जो तमाम इन्वेस्टमेंट है ये एक्चुअली इसलिए है कि लोग किस तरह अपनी टाइम और अपनी जो सोच है उसको कन्वर्ट कर सकें इनटू समथिंग दैट इज यूजफुल. लेकिन उसके कुछ प्रोसेसेस हैं, क्योंकि जो लोग बाहर काम कर रहे हैं उन्होंने वो चीज़ें देखी हुई हैं, तो दे कैन एडवाइज यू कि किस तरीके से आप ये काम कर सकते हैं, विच हैज़ ए गुड चांस ऑफ बीइंग सक्सेसफुल. ये जो कॉन्ट्रैक्ट हाउस का मॉडल है ये ईस्ट यूरोप में, इंडिया के अंदर इट हैज़ बीन सक्सेसफुल, और फिर दे वर एबल टू पुट टुगेदर देयर ओन सॉल्यूशंस. लेकिन it is शुरू में it's usually hard.
So, any more questions? I think there is no more question, and it's a deep late night in Texas. Dr. Kurum, thank you very much for your time.